An equation with two variables has an infinite number of solutions. However, given a different equation with the same variables, chances are you can find a solution. Let's look at three different algebraic methods for solving a system of two equations with two unknowns. The substitution method, which involves substituting one of the equations into the other. The like coefficients method, which involves adding or subtracting the equations from each other. And the slightly more challenging determinant method, which, unlike the other two, has a formula for the solution. Welcome. A speedboat on a river travels 15 km per hour downstream and 7 km per hour upstream. We can calculate the boat's and the current speed by constructing two equations with two unknowns. Going with the current, the sum of the boat speed x and the current speed y equals 15 km per hour. Against the current, the difference between the boat speed and the current speed is 7 km per hour. With the given information, we've constructed two equations with two unknowns, also known as a system of equations. Two or more equations with the same variables make up a system of equations. More specifically, this is a linear system of equations because it is made up of first-degree equations with a highest power of 1. Two points from the previous video on equations also applies to this one.
I denne video skal vi kun beskæftige os med førstegradsligninger. I en førstegradsligning er den ubekendte opløftet i første. Ligningen i eksemplet er en førstegradsligning, fordi der er et x eller et x i første.
Let's solve the two equations using the substitution method. The idea is to use, for example, the first equation to express x in terms of the other variable y, and substitute or replace this result into the other equation. Rewriting the first equation, we get we substitute this into the other equation, so it says 15 minus y instead of x. The resulting equation now only depends on y. So let's solve it for y. This gives negative 2y, and let's move 15 over to the other side. Negative 2y equals negative 8, and dividing by negative 2 on both sides gives y equals 4. Which we now substitute into the first equation to find x. The boat speed in still water is then 11 km per hour, and the speed of the current is 4 km per hour. We can check the solution in both equations. Therefore, the solution is the number pair x equals 11 and y equals 4. Here are two different ways to express the solution. This is the mathematical symbol for AND. These are the steps in solving a system of equations using the substitution method. 1. Isolate a variable in one of the equations. 2. Substitute the expression in the other equation and solve for the other variable. 3. Substitute this value in the equation in step 1 and solve. 4. Check both values in both equations. This method is most convenient to use when the coefficients of one of the variables is positive or negative 1. When a term has a constant multiplied by a variable, the constant is called a coefficient. For example, the coefficient of 5x is 5, and the coefficient of negative 2q is negative 2. In this problem, all of the coefficients are positive or negative 1, because there is an invisible or understood 1 coefficient in front of x and y in the equations. Let's look at an example where none of the coefficients are 1. And let's isolate b in the first equation. And substitute this in the other equation. We can solve this equation for a, but it's going to be a bit of work. And that's because we used the substitution method despite none of the coefficients being positive or negative 1. Let's instead use another method. In this method, we also want to obtain an equation with only one variable. We can do this by either adding or subtracting the equations from one another. But before doing so, it might be necessary, as is the case here, to rewrite one or both of the equations such that the coefficients of one of the variables is either the same or opposite in both equations. If we multiply the second equation by 2 on both sides, a's coefficient becomes negative 10. We can eliminate a by adding the second equation to the first. As you can see, the left-hand side of the second equation is added to the left-hand side of the first equation, and the same has happened on the right-hand side. The plus parentheses can be omitted. 10a and negative 10a cancel out, and 3b plus 8b equals 11b. The sum on the right-hand side is 77. b is therefore equal to 7. With this b value, we can substitute 7 in one of the equations to find a. Substituting in the second equation gives negative 5a plus 4 times 7 equals 23, which can be solved for a. Alternatively, we can repeat the process and eliminate b instead. To make b's coefficient the same in both equations, it's similar to finding the common denominator of two fractions. A possible like coefficient for b is the product of the coefficients. 3 times 4 equals 12, which can be obtained by multiplying the first equation by 4 and the second equation by 3. Let's subtract the second equation from the first. The minus parentheses is removed by switching the signs of the terms inside the parentheses. Negative 15a becomes positive 15a, and positive 12b becomes negative 12b. These terms cancel each other out, and 40a plus 15b equals 55a. On the right-hand side, the difference is also 55. Therefore, a equals 1. We have the solution a equals 1 and b equals 7, which we can check in the original equations. Using the same system of equations twice, we've rewritten one or both of the equations such that the coefficients of one of the variables are numerically the same. First for a, then for b, and then eliminated that variable by adding the equations when the coefficient signs were opposite, and subtracting the equations when the signs were the same. And finally found a number pair which solves the two equations. These are the steps in solving a system of equations using the like coefficients method. 1. Rewrite the equations such that one of the variable's coefficients are numerically the same. Numerically the same means that the coefficients are the same except for the sign. 2. Add or subtract the equations to eliminate a variable. 3. Solve the resulting equation for the other variable. 4. Substitute or repeat the process to find the first variable. 5. Check both values in both equations. Using a similar approach as the like coefficients method, we can exemplify another method, a theorem, which has a formula for the solution. Let's solve these two equations, and let's first eliminate the variable q in the first equation. Multiplying the first equation by 9 and the second equation by 4 gives like coefficients for q. Nine and 4 is multiplied onto each term in the parentheses. I am purposefully not calculating the products here. Q's coefficients are equal, so let's subtract the second equation from the first. This parenthesis is removed by switching the signs of the terms inside, and the two Q terms cancel out. Since P appears in both terms on the left-hand side, the left-hand side can be factorized. Dividing by the parentheses on both sides isolates P. Let's finally calculate the value. 18 minus 4 is 14, and 27 minus 20 is 7. And 14 is divisible twice by 7. The fraction we derived for the unknown P here is the same we would get using the determinant method. We can use the formula to find Q because the system of equations in the problem is on this form. That is, two linear equations with two unknowns where the variables are on one side of the equation and the constants on the other. The examples in this video have actually all been on this form. In other problems, however, you might have to rewrite the equations a bit to get it on this form if you want to solve it with the determinant method. Let's compare what we derived with what the formula says. In the problem, P corresponds to X. And according to the formula, P is given by the fraction 2 times 9 minus 1 times 4 divided by 3 times 9 minus 5 times 4. So it checks out. Let's use the formula to calculate Q, corresponding to using the like coefficients method to eliminate P followed by isolating Q in the second equation. The denominator is the same, but the numerator looks a bit different. Three minus 10 is negative 7, and the denominator equals 7. Negative 7 divided by 7 equals negative 1. We can check the values in the original equations. This is called the determinant method because the numerator and the denominator here corresponds to calculating these determinants. Determinants is a subject for another video. However, this formula is a special case of Cramer's rule, which we will explore a bit in the discussion coming up. In maths, we'll often come across two equations with two unknowns. Most notably, perhaps when deriving two-point formulas for the slope, common ratio, and power of, respectively, linear, exponential, and power functions. Given two general points, x1, y1, and x2, y2, both a linear, exponential, and power function going through these 2 points can be found. The graph shows the three functions and their expressions. The slope of a linear function passing through these points can be found by solving the following two equations. This system of equations comes from substituting the points in the general form. And this is the solution. The systems of equations for deriving the common ratio of the exponential function and the power of the power function are obtained in a similar fashion. Here they are along with their solutions. The unknown b in all cases is found by substituting the value for a in either of the original equations. A system of equations also have a graphical representation, which we will return to in another video. It is, however, important to note that an equation with two variables like this one can be considered an expression for a linear function, since it can be rewritten to the same form as the general linear function. One equation with two unknowns, such as this one, does not have any one solution. As a matter of fact, it has an infinite amount of solutions, which are represented by every point on this line. The equation can be solved given another equation with different information. The solution then, graphically, is the intersection between the two lines. And this actually goes beyond a system of just two equations. Two unknowns can be found with two different equations, three unknowns can be found with three different equations, and n unknowns can be found with n different equations. Different in this context means that the equations are not equivalent. Take, for example, the two equations here. At first glance, they do look different. However, the first equation is equivalent to the second, since they become identical if we multiply the first equation by 3. Therefore, the second equation provides no new information, and we can think of the two equations as representing two coinciding lines. It bears noting that a system of different equations does not necessarily have a solution. That case would represent two parallel lines that are shifted with respect to each other and therefore won't ever intersect. But what if, say, we have three equations with two unknowns? More information should, in theory, be better, right? Going back to our previous example, let's consider this third equation. Its graph looks like this, and now there is no one intersection between the three lines, and therefore no solution. The third equation is inconsistent with the first two. Let's instead take this as our third equation. Its graph looks like this, and now all the lines do intersect in the same point, so the number pair -2, 3 is still the solution. However, the information added here by the third equation changes nothing and is therefore redundant. More equations than there are unknowns has no benefit, as it either constitutes an inconsistent system of equations or one equation is redundant. In the two equations with the two unknowns, x and y, we might rename the variables to x1 and x2. And write this system of equations on matrix form. This is a matrix, the coefficient matrix, and these are column vectors with the variables and with the constants. A matrix is a rectangular array of numbers. The number of rows and columns determine the dimensions of the matrix. The coefficient matrix is a 2 by 2 matrix. The study of matrices is a large part of linear algebra, but here we're just going to need the coefficient matrix. And let's name it A, the variable vector x, and the constants vector b. Then the system of equations is on the form a times x equals b. We saw when going over the determinant method that the variables can be calculated by dividing certain determinants. Do you recognize the determinant in both of the denominators? That is the determinant of the coefficient matrix. The determinant in the numerator, however, is the coefficient matrix with the first column replaced by the constants vector when calculating x, whereas the second column is replaced by the constants vector when calculating y. So x1 in this problem, according to the determinant method, is given by which is equal to -2. This also holds for a system of n equations with n unknowns, and that is the contents of Cramer's rule. So a system of n linear equations with n unknowns on this form with a coefficient matrix which has a non-zero determinant. Each element of the solution can be calculated by this fraction. So if we want to find x2, Cramer's rule states that it's the determinant of a2 divided by the determinant of a. The A2 matrix is then the coefficient matrix A with the constants vector substituted for the second column. And this equates to 3. Let's look at an example with 4 equations with 4 unknowns. A loaf of bread is made from 1 kilo of ingredients and is 55% carbohydrates, 21% fats, and 10% protein. There are 4 main ingredients: flour, wheat bran, wheat germ, and margarine, the nutrients of which can be looked up in a table. The numbers are in mass percentages, and what's rest is water. The ingredients with their individual nutrients combine in some unknown way such that the sum of the ingredients is 1 kilo, the sum of the carbs is 55%, the sum of the fats is 21%, and the sum of the proteins is 10%. We can combine this information in 4 equations with 4 unknowns. Where x1 represents the mass of flour, x2 the mass of wheat bran, x3 the mass of wheat germ, and x4 the mass of margarine. We can calculate all the unknowns using Cramer's rule. For example, x1 is given by this fraction. Where the determinant in the denominator is of the coefficient matrix and the determinant in the numerator is of the coefficient matrix with the first column substituted with the constants vector. The answer is half a kilo of flour. Repeating the process gives the result: 210 grams of wheat bran, 63 grams of wheat germ, and 220 grams of margarine. These numbers is the solution to the systems of equations. The next video will be about the quadratic equation, how we go about solving it with the quadratic formula, and how we prove that formula. If you like this video, give it a like and subscribe to the channel. Thanks for watching.